Welcome back to the course on statistical mechanics of phases and phase transitions. In this lecture, we'll continue the first chapter, which is the introduction to the subject. So let me begin with a brief summary of the previous lecture. So the main thing that we saw in the last lecture was that when many degrees of freedom, such as atoms, molecules, electrons or spins or whatever, qubits, when they come together and interact, they will organize themselves into phases. And distinct phases can be realized by the same set of degrees of freedom depending on conditions such as temperature and pressure, etc. Phases can be separated by phase transitions. Phase transitions can be first order or they can be continuous. First order transitions are characterized by an abrupt change of properties, such as the change of density of water across the freezing transition. Typically, these first order transitions are accompanied by latent heat. Continuous transitions are more interesting in that they have a certain set of properties which are characterized by a continuous change from one phase to the other. For example, if I look at this antiferromagnetic material, dysprosium aluminum oxide, it's called a garnet, you will see that when I look at the magnetization above the so-called nail temperature, you will see that the staggered magnetization is 0. Below the nail temperature, the staggered magnetization abruptly starts to increase, but starting from 0, and then it very quickly increases all the way up to 1. These are characterized also by a divergent specific heat and a divergent magnetic susceptibility. These divergences can be characterized by certain critical exponents, as we had seen in the last lecture. So for example, if you parameterize the temperature by some dimensionless ratios such as this reduced temperature T minus Tc divided by Tc, then the magnetization will diverge with this reduced parameter by an exponent beta with coefficients C beta plus minus. Plus stands for above Tc and minus stands for below Tc. Similarly, Cv does the same thing with another exponent called alpha, conventionally defined with a negative sign, and the susceptibility does the same thing with an exponent gamma, and these constants are dimensionful parameters depending on what quantity one is measuring, and they are different on the plus side and minus side of the transition. So these are called critical exponents, and the ratios of C plus by C minus are called amplitude ratios. So the most beautiful thing about continuous phase transitions is the idea of universality. So if I take the data, experimental data for a variety of systems near the liquid gas transition and plot them in dimensionless terms, temperature by the critical temperature, remember critical temperature for all of these things will be different, but T by Tc is a dimensionless parameter, and similarly rho by rho c is the critical density, you will see that all the data for different materials will collapse into the same curve. And this is exactly what we mean by universality. So in the sense that the second order phase transition viewed from these dimensionless parameters seems to forget what the constituent materials are made of, what this system is made of. The second interesting thing is that these universalities fall into different universality classes. So for example, these three systems here fall into what is called as the Ising universality class. This system of helium-4, it falls in what is called as the XY universality class, and Fe and nickel magnetic transition falls in what is called as the O3 universality class. So they fall in different universality classes, and each universality class is characterized by a set of critical exponents which are sort of properties of those universality classes. The critical exponents can be different in different universality classes, but the remarkable thing is that across the universality classes, they satisfy the scheme, they satisfy a set of rules called as scaling laws. For example, alpha plus 2 beta plus gamma will be 2. Okay. So these are the puzzles that we would like to resolve and understand in this course. So how to describe phases. We would like to learn analytical numerical methods to study phases. And in particular, we would like to understand how to uncover the universality that is present in these second order phase transition, and this will be covered in this topic called as the renormalization group. So what are the prerequisites we would like to have before we go ahead? So the participants of this course are expected to know a good amount of classical mechanics and some foundational quantum mechanics, but typically dealt with at the undergraduate level. And very importantly, one has to have exposure to elementary thermodynamics and statistical mechanics. So to enable a smooth discussion going forward, we will in the remainder of this lecture review the prerequisites for the course. So the plan of the review is we will first discuss how to describe physical phenomena and what are the ways of describing physical phenomena. We will then review a bit of thermodynamics. We will go on to review some statistical mechanics. And at the end of this lecture, we will make our first attempt to construct a phase diagram. And let's see how successful we are. Okay, so let's start with trying to understand how to describe physical phenomena. So typically we observe physical phenomena on various scales. So we have till so far we have observed from a scale such as the quark scale all the way to, let's say, the early universe. So we have observed nature on all these scales. So there are several different types of approaches to go ahead with the description. One is you could stay at a particular scale such as our terrestrial scale, which is of the typically a meter scale. We make observations, and based on these observations we make what we call as a phenomenological theory. We try to find what rules nature is following without worrying about where those rules came from, and we try to use those rules to make predictions. So this approach is called as phenomenological approach. So here, as I said, let's observe nature on the 1 meter scale, then make a phenomenological theory using the observations, and then make certain predictions based on the phenomenological approach, and this is the idea of the phenomenological framework. A very good example of such a theory is classical thermodynamics. The laws of thermodynamics were discovered by a lot of experimentation and a lot of hit and trial. Once they were formulated, we were able to use them to design engines and make the industrial revolution possible. The other approach is the microscopic approach. So going back to this picture, we would like to understand how liquids and gases form starting from atoms. So what we do is we look at, if you want to describe phenomena, let's say at our scale of 1 meter, we will look at what nature is made of at a different scale, such as the atomic scale. And we would start with the microscopic degrees of freedom, which are present on the atomic scale, and we will use physics from this atomic scale and the interactions between atoms, etc., to make predictions of what would happen if these large number of degrees of freedom interact with each other and form phases, etc. So a very good example of this is things that you would have studied in your high school, kinetic theory of gases, and in your undergraduate program you might have studied statistical mechanics. So this is also typically a microscopic approach. So these are the two ways you can approach nature, and you will see that we will sort of use both these ideas to come up with ways to understand phases and phase transitions. Okay. So let's first start discussing thermodynamics, which all of us have seen in our undergraduate study. So, thermodynamics is encapsulated in a set of laws. The zeroth law of thermodynamics says that there is a notion of equilibrium. So, if a system is in equilibrium and you do not disturb it, it will stay in equilibrium forever. And the second thing it says is that if two systems are in equilibrium and in contact with each other, one can say that they have the same temperature. So, it introduces a concept of temperature which characterizes equilibrium. Moving on, there is the first law of thermodynamics. First law of thermodynamics introduces the concept of energy, and it says that energy is conserved. One form of energy may be converted to other, but the total energy cannot be changed. It goes on to say that energy comes in the form of heat and work, and energy can be stored in the system by what is called as internal energy, and the law of conservation of energy is put down in this following fashion, that if you add some heat to a system, that added heat can change the internal energy of the system, and the system can do some work as well. Moving on, second law says that what are the spontaneous processes that are possible. Two processes that satisfy energy conservation, they both need not be spontaneous. In fact, there are many processes in which energy is conserved, but they do not spontaneously happen. For example, you do not see me just cool down and rise up, so my internal energy reduces and that is change of my potential energy. That is not spontaneous, it does not happen. And the way this is described is by introducing a concept of entropy, which is a property of the system. And the main idea of second law of thermodynamics is that spontaneous processes will not reduce overall entropy of the system and the surrounding. This is what the second law essentially says. So, typically in undergraduate programs, we are taught this by an inequality called as the Clausius inequality, which means if you take a system in a cycle where the system is brought back to its original condition, the total infinitesimal heat divided by the temperature at the point of heat transfer, if you take this integral around the cycle, this will be less than or equal to 0. So, this is the second law of thermodynamics. Okay. All of this culminates in bringing us the concept of thermodynamic potentials. To understand thermodynamic potentials, let us put the second law and first law, all the laws in a sense together, and write the law of in this form. So, it says that TdS, the change of entropy, is in some infinitesimal process, is greater than or equal to the change of internal energy, the work done by the system, and I have also taken the liberty of being able to change the number of particles in the system and introduce the concept of the chemical potential here, which is denoted by mu. P is the pressure and T is the temperature, as we have already seen. Now, the interesting thing to observe is that in this equation, there are certain things that you see. There is T, P and mu. These are quantities that do not depend on the size of the system. They are intensive quantities. On the other hand, the entropy, energy, volume and number of particles, they are extensive quantities in the sense that they depend on the size of the system. So, I invite you to show that using this idea that certain quantities are intensive and certain quantities are extensive, you can show that the energy can be expressed in terms of temperature, absolute temperature, entropy, pressure, volume, chemical potential and particle number in this fashion. So, I invite you to check this. Okay. So, thermodynamic potentials are what are the outcome of the laws of thermodynamics, and they are very natural ways to discuss systems, in the sense that a system kept in a certain set of conditions, for example, if you keep the system at fixed energy, volume and particle number, then there is an associated thermodynamic potential, in this case the entropy, which is maximized. So, any process that preserves energy, volume and particle number, if it has to occur, then the entropy has to increase. For example, free expansion of a gas. So, now I invite you to show that if I isolate a system, this entropy is maximized. Okay. There are many other thermodynamic potentials and they are also called free energies. I will just review a few of them which we will be using in the course. So, the first one is the Helmholtz free energy. It is typically denoted by the symbol F, and the fixed parameters in this case are temperature, volume and particle number. And the free energy, Helmholtz free energy, is related to energy and entropy and temperature via this relationship. Similarly, there are other free energies. I am just writing a couple of them down here. The Gibbs free energy, this is when a system is kept at a fixed temperature, pressure and particle number, and that is the Gibbs free energy. And there is also something called the Grand potential, which is when the system is kept at fixed temperature, volume and chemical potential, and this is the expression for the Grand potential. Okay. So, you will see that as we go into this course, we will be discussing magnetic systems quite a bit, because they are also a very interesting playground for studying statistical mechanics. So, I would invite you to work out what are the thermodynamic potentials for a magnetic system. So, in a magnetic system, for example, there will be different parameters instead of V. For example, you will have a magnetic field, and you can try to work out what are the thermodynamic potentials for the magnetic system. Okay. Now, we would like to understand how can we use the phenomenology that we have studied, namely thermodynamics, and how can we view phases and phase transitions from that perspective. So, the first thing we have noted is that given some set of conditions, the system will realize a state which optimizes the free energy corresponding to those conditions, free energy or thermodynamic potential that corresponds to those conditions. For example, if you fix T, V and N, as we saw in the last slide, the Gibbs free energy is minimized, and the state that is realized, say for a set of interacting atoms, will be a state such as solid or liquid or something like that. So, the point I would like to make in this slide is that the phase transitions occur when the free energy has some kind of non-analyticity. This is the phenomenological statement. This is how we are going to capture the phenomenology of the phase transition in this framework of thermodynamics. So, what do I mean by non-analyticity? So, let us first look at first order transitions. So, you can get a first order transition when I have a transition from a solid to a liquid crossing the line that I am showing here on the slide here. So, if I cross this line, I have a first order transition. So, what happens at a first order transition is that, let us say if the temperature is below T, the melting temperature, solid going to liquid, you will see that the free energy of the solid is lower, the Gibbs free energy of the solid is lower, and at the melting temperature you will see that there is a change of track, as it were, and you will see that the system will follow this line as the lower free energy line. So, there is a melting that takes place. So, there is a change of phase because the solid has a lower free energy below T melting and the liquid has a lower free energy greater than at temperatures greater than T melting, and so there is a change of track. And what this would mean is that there is a change in the slope of the free energy at the melting point, at the melting transition. So, this is what I mean by some kind of non-analyticity or some sort of singularity in the free energy. Okay. So, now all of these lines here, the ones that I am showing, they are all first order lines. So, they are all characterized by very similar kind of phenomena, like some derivative of the free energy changes. But the most interesting aspect is this point here, which is the critical point. where if I am at this pressure, for example, I change the temperature, I will be in the liquid state. Without any abrupt change of density, I can transition into something like a gas state. And this happens via a continuous transition. This point has a continuous transition, and this first order transition line ends at this continuous transition point. Sorry. So what happens there? There, the free energy will, this sort of free energy will be smooth. There in the say it will be continuous. It will sort of not have any change. Its first derivative will not have any change, but its second derivative will have a divergence. And that is the specific heat, and that's what I'm showing you here, and it will have a divergence. So what happens is that higher derivatives have singularity in this continuous phase transitions. So the main idea here is that phenomenological descriptions of phase transitions within the framework of thermodynamics is captured by some sort of non-analyticity of the free energy as a function of the parameter which causes the phase transition. And this could be first order, where there is a change in the first derivative of the free energy, or it could be a continuous phase transition where some higher derivative, typically the second derivative of free energy, has some sort of singularity, as is shown here. Okay. So this is what the thermodynamic view of phases and phase transitions. Okay. Having seen the phenomenological view of phases and phase transitions, we will now quickly look at how to think about phases and phase transitions from a microscopic perspective. So this is where we will review statistical mechanics. So statistical mechanics, as we have already discussed, is a microscopic approach. So we start with a set of degrees of freedom on a scale which is much smaller than where we want to make observations, like our scale of a meter. And we ask, how can we, for example, get the equation of state of a gas, starting from the fact that nature is made of atoms which are moving around at a certain temperature and so on. So the key idea of statistical mechanics, as opposed to conventional Newtonian mechanics or quantum mechanics, is not to solve the dynamics of all the degrees of freedom. So for example, if I want to solve the equation of state of the molecules in this room, I will not start from the positions and momenta of all the molecules in this room and try to map out the trajectory as a function of time and measure some observables from those trajectories, etc. That's the dynamics approach. So the idea of statistical mechanics is to give up dynamics, but instead adopt a probabilistic description. So what do we mean by a probabilistic description? Suppose C is some microscopic state of the system, say for example some positions and momenta of all atoms. Then the macro state of the system, that is the conditions under which you are keeping the system, will describe a probability distribution of over the set of microscopic states. So what we are going to do is we are going to say that if you give me the set of all microscopic states, there is some probability distribution P of C which tells you what is the probability that a microscopic state C is realized given a set of macro conditions that we are specifying, such as temperature, pressure, etc. Now, if the system is in equilibrium, then the rules of statistical mechanics tells you that all the configurations, all the microstates with the same energy are equally likely. And this then allows us to define the probability of a microscopic state as 1 divided by z exponential of beta times h of c. So h of c is what we call as the Hamiltonian of the system, and it tells me what is the energy associated with this configuration. Beta is 1 by temperature, and I should point out here that throughout this course we will choose units in which temperature also have units of energy, and that is equivalent to saying that the Boltzmann constant is set to unity. This simplifies our notation, and we can always put back Boltzmann constant whenever we need. So, we will adopt this simplified notation, if you like. And Z here is the partition function, that is, it is the sum over all configurations, the weights of these configurations, namely e to the minus Hamiltonian of the configuration divided by temperature, and beta is of course 1 by temperature. So, this is essentially the postulate of statistical mechanics, that if you keep a system at constant temperature, volume, number of particles, something like this, then you will see that the probability of a microstate is given by this expression. Once we have this, we can immediately connect to the phenomenological thermodynamics that we have seen in the last part of the lecture. So, connection to the phenomenological description is the following. So, if you keep this system in the way that I have described, it is called the microcanonical ensemble, which many of you will be familiar with. The Helmholtz free energy can be obtained from the partition function by taking the log of the partition function, multiplying with temperature with a negative sign. So, this is our connection to the phenomenological thermodynamics. So, what would be a strategy now? The strategy for us is, we would try to find out what are the Hamiltonians, etc. for our system, how do we describe the system, what are the configurations of our system. We will try to compute the partition function, and we would then find the free energy, and once we find the free energy, we can look for set of parameters of, say, external conditions where the free energy has some kind of non-analyticity, and that will give us a window into understanding phase transitions. And the equilibrium states which are away from phase transition points, they will be describing phases, and therefore, by studying these free energies in these places where system has free energy that is analytic or smooth, we can study even phases. So, this is the idea. Okay. So, let us just see this in action a little bit. So, let us consider a system of classical particles. Let us say there are n particles, each of mass little m, and they are interacting by some kind of potential, they are interacting pairwise in a box which is in d spatial dimensions. So, it is some kind of d dimensional cube, if you like, whose edge is of size L, and with periodic boundary conditions. So, the configuration space C is the set of all positions of the particles and the set of all momenta of the particles. This is how we describe configurations of many particle systems in classical mechanics. So, the canonical partition function now can be written as the sum over configurations, because these are continuous variables, now become integrals, and we can write down the partition function as 1 by h to the, h is Planck's constant by the way, to the space dimensions times n by n factorial. These are needed for introducing indistinguishability of classical particles. This is of course, this h is needed for dimensional considerations, this n factorial is for the indistinguishability. And you will be able to now go through exactly the same formula that I had discussed in the previous slide, with this sum over configurations being replaced suitably by these integrals. So, you will see that this is the partition function, and the Hamiltonian now is the kinetic energy of the set of all particles and the interaction energy between particles. So, U is the pairwise interaction potential, and this quantity is the distance between the particles. Okay. So, the free energy for a system with n particles you can immediately obtain by taking the log of the partition function that we have, and then this contains all the information about the system, including the phases and phase transitions that it has. Okay. So, we have done this for the canonical ensemble. So, I will briefly mention that we can also work in other ensembles where, for example, we can fix the chemical potential instead of the number of particles. We can then construct the grand canonical partition function, which is the following. you sum over all possible particle numbers in the system and compute the partition function associated with some particle number n, and then multiply the partition function of with n particles by this quantity e to the beta n times beta e to the n times beta mu, where mu is the chemical potential. Now the grand potential, which we had seen in the last couple of slides, can be related to the partition function, this grand partition function, via this relationship. And mu can be determined by solving the equation. If you had n particles on an average, you can solve this equation, and this will find the value of mu corresponding to the system where on an average in your system you have n particles. Okay. So you may wonder, oh, but how can this all be true? Because nature has also quantum mechanics. So how do we do quantum statistical mechanics? Let's briefly review that. So for quantum systems, their configurations are actually described by a state in something called a Hilbert space, which is in a sense the collection of all possible states of the quantum system. It is a complex vector space. And the Hamiltonian is described by a Hermitian operator, which we will denote by this H here. So statistical mechanics now postulates that the state of the system, the probabilistic state of the system, is described by something called as a density matrix, which I have written here using bold rho, and this is determined by the macro state of the system, the conditions under which you are keeping the system. So what does this density matrix, what are the properties of the density matrix? First, it is a Hermitian matrix or a Hermitian operator. Second, the trace of this operator, namely the sum of the eigenvalues, turns out to be unity. So you can see that the eigenvalues of these operator have some nice property that they will add up to 1. Okay. I must also mention that this will be a positive definite operator, and that will give this operator a meaning of a probability, if you like. So the expectation value of any observable now can be obtained by tracing the product of this density matrix with the operator of your interest, and this allows the computation of any observable O. So if I now go to canonical ensemble, where I keep the system at a fixed temperature, say, then the rules of quantum statistical mechanics will tell you that the density matrix goes as 1 by partition function, sum over all states n. What are n? The states n are the eigenstates of the Hamiltonian. So these are the energy eigenstates. So you sum over all the energy eigenstates, and this is the projector. This ket n bra n, this quantity is a projector into the subspace containing the nth eigenstate, and you multiply it by this weight. The weight is e to the minus beta times the energy eigenvalue corresponding to the state n, and the partition function is exactly the sum of these weights, these thermal weights as they are called. Okay. So this is the canonical ensemble density matrix. So now if you see what is the observable is, suppose I take the trace over the canonical density matrix, you will see that that can be written in the following way. It is Pn, and what is Pn? Pn is in a sense the statistical probability of realizing the state, if you like, and this quantity is the quantum average or the quantum expectation value of this operator on the eigenstate n. So you can interpret this equation very qualitatively and nicely, that the observable value, the value of the observable is the thermal average of the quantum average. Once you get this partition function, you can again compute the free energy, like the Helmholtz free energy that we discussed, and that will be given by this equation. Okay, so now that we have reviewed this, you should pause the video and try to answer this question. Suppose everything else is the same, which of the following three systems will have the highest pressure at a given temperature? The classical distinguishable particles, indistinguishable particles, fermions or bosons. So there are three systems here given here: classical indistinguishable particles, fermions, these are quantum particles, they obey Pauli exclusion principle, or bosons, where remember bosons, more than one boson can occupy a site. Which of these will have the highest pressure at a given temperature? Please try to think about this before proceeding. Okay, so now that we have laid out all this phenomenological and microscopic framework, we should try to see whether, based on some simple calculation, whether we can try to get a phase diagram of some system. And the simplest system to work with is the classical ideal gas. And the nice thing about the classical ideal gas is that the statistical mechanics of classical ideal gases can be solved exactly. Okay, so you can work out the canonical partition function. This involves doing a bunch of Gaussian integrals. I strongly encourage you to do this. So this is the partition function with n particles, and that turns out to be this quantity. So it is 1 by n factorial, the volume of the system divided by lambda, which is a function of temperature, to the power d. So notice that this is a dimensionless quantity. This is a volume and lambda is a length. And that length is given as a function of temperature by this quantity, which is called as the thermal de Broglie wavelength. So this is the canonical partition function. So just imagine you have a very large number of particles, but it has the partition function that has such a very nice and simple expression. So if you compute the free energy density, you will see that the free energy density looks like this. In computing the free energy density, I have used something called as the Stirling approximation for n factorial, which is good when n is a very large number, and typically we have an Avogadro number of particles. So this is a good approximation. So this is the free energy. Okay, now you see, we see something very interesting in the expression for free energy. If we are looking for a phase transition of some sort, then we should look for a point at some finite temperature where this free energy has some kind of non-analyticity or some kind of discontinuity or in its derivative or whatnot. But if you study this carefully, you will see that this has no such non-analyticity at any finite temperature. So in particular, the ideal gas cannot describe the liquid gas phase transition. And so this turns out to be a very important lesson for us, that in the classical ideal gas, there are no interactions between particles. What we learn from all these considerations is that interactions are absolutely critical for forming distinct phases starting from some set of constituents. If it were not for interactions between the degrees of freedom, the word would be far more boring and there would be probably just a single phase. So it's interactions between particles that produces all the nice physics that we see. So I did make a statement that ideal systems cannot have distinct phases. So now I invite you to think about this a little bit more. So can there be a finite temperature phase transition in a non-interacting many particle system with quantum mechanics? So I invite you to think about this question. Okay. So we have come to the end of this lecture, so it's a good time to summarize what we have done in this review. So the key points are the following. The course goal is to understand phases and phase transitions. There are different ways to describe physical phenomena that we see. There is the phenomenological approach, there is the microscopic approach, and the example of phenomenological approach we saw is thermodynamics. So thermodynamics hinges on the uses of different types of free energy depending on the conditions under which the systems are kept. These are called thermodynamic potentials of free energies. Phases are realized by optimizing the appropriate free energies. Phase transitions are characterized by some kind of non-analyticity in the free energy as we change some parameter in the system. And then we looked at microscopic approaches and this was achieved by looking a bit at the statistical mechanics, which I assume that you have seen in some form or the other in your previous studies. So statistical mechanics is a probabilistic approach, and the partition function of classical and quantum systems allow you to connect this to the thermodynamic or phenomenological quantities that we are aware on our scales. So this is how we make the connections between microscopics and macroscopics, and we also try to compute the phase diagram of a set of atoms, and we started off with a simple model where we ignored the interactions between the atoms and we failed in producing a phase diagram. And what we learned was that interactions are absolutely essential to produce different types of phases. So I look forward to seeing you in the next lecture.